Faculty Wednesday. We did the distribution of means last time. I think that's where we ended, right? Next up is distribution of proportions. Random sample size n is obtained from a population in which each individual either does or does not have a certain characteristic. Kind of sounds like the binomial distribution. Sample proportion is p hat, and it's the number of individuals in the sample with the specified characteristic divided by your sample size. Clearly, this is just a statistic that estimates the population proportion. For a simple random sample size n with a population proportion p, shape of the sampling distribution is approximately normal, provided that NP is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. The mean is given by just p. Standard deviation, square root of p times 1 minus p over n. And then z-score if you need the z-score, p hat minus mean all over standard deviation. find the probability that in 120 tosses of a fair coin, less than 40% or more than 60% will be heads, and that 5/8 or more will be heads. Clearly a proportion. So remember, mean is going to be the population proportion P. Which is what? What is the population proportion?
Yeah, we are with voice again. Less than 4.
So you toss a coin. What is the expected proportion of heads? 1/2, 0.5. Standard deviation. P, or square root of P times 1 minus P over N. What's 1 minus P then? 0.5, this one's easy. And what is our sample size? And
I know I'm really right, but what is this type of distribution? What kind of distribution is this?
proportions. You should get about 0.0456. That's what we're going to stick with. First probability we're looking for, between 40% or less than 40 or more than 60. First, we need the z-score for 0.4. Now for 0.6, you shouldn't need a calculator. It's going to be positive 2.19. Oh, that's nice.
Yes, we're gonna need a table for it.
We're going to need a table. We're going to need that table, so I'll bring that up. We're looking for the probability that p hat, they said what, less than 40? Yep. Or greater than 0.6. In this case, well, in fact, for all proportions, your events are mutually exclusive. Right, there's going to be no overlap between less than 0.4 greater than 0.6. So it's just the sum of the individual probabilities. Same as that, right? Convert to z-scores. Oh, but we're symmetric about the mean. So the area to the left of negative 2.19 and the area to the right of positive 2.19 is the same. Which area would the table give us? Left of negative 2.19 or to the right of positive 2.19?
Do we have to visualize this one too?
I mean, if you want to, you can.
Oh, last thing.
So what does our chart give us? us area to the left or area to the right as a value?
Which one?
I'm just saying the chart. What does the chart give? Area to the left or area to the right?
In terms of those figures?
No, just in general. Does it give area to the left or to the right? To the left. So that's the one I'm going to keep and double it. Now go to the chart. Negative 2.19. It's negative 2.1, and mine is all the way over. So it's that one right there. Double it 0.0286, which is 2.86% chance. So not very likely. Second part, 5/8 or more. Z-score for 5/8. Can we turn that into a decimal? Deviation is 456. You don't need to. When you enter into your calculator, it's going to convert it to a decimal for you.
I'm lost.
2.7.
What was it?
2.7.
Where?
I'm confused about everything.
Like, how did we derive a 0.4? That's the problem. It's 0.4 or
That's what I was asking for.
that's the problem there, right? Okay. And okay, so now the negative 2.19, how did it come about?
That is the Z-score.
Is this go?
Is can we start?
Is this for question one still?
And so remember, always convert to Z-scores. We always do standard normal.
Yeah.
remember our chart gives us less than. We want area to the right. So 1 minus area to the left. So let's find 2.74.
.9969.
Which is 0.0031.
Got my calculator, so.
0.31% chance.
How did you get that?
Yeah, what?
0.31?
That was after subtracting 1 minus.
Oh.
The percentage or the actual .0031? To find percentage, I just multiply that by 100.
Oh, okay.
So I observed one thing. I didn't read the question over. This one mostly come about it's above, right? Of paper.
When what's above?
And like when the problem asks for like something like that is above the means or greater than the mean.
Well, if it's above, you always have to do the 1 minus, right? Because the chart only gives area to the left,
That's for greater too.
Yeah, that's
which
why,
is greater, yes.
that's what I'm trying to say. Like whenever you, that's what I realized. Whenever it's in a greater or above, that's when
It has to be 1 minus because
1
we only get area to the left in this chart.
Yeah.
There are some charts that give area to the right, not ours.
That's what I'm trying to remember.
Some charts give area between.
Yeah, between that's when you subtract both, right?
Well, I'm saying there are charts out there that also that will give you area
Oh,
between the mean
okay.
and a z-score instead of right or left. So for our charts, it's always area to the left. So this is what we're sticking with.
Okay.
If you take another stat course, you might get a different chart. So it might be different
Ooh.
based on that.
Thinking stats. This is a thought check right here.
The top part.
Sorry, so on the right side, you see where you have the answer. When I see it at the top, we work it out.
This bit
Okay. Yeah, like in the second part,
here.
to the right. Yeah. Yeah.
Well, we want probability that we get more than 5/8 heads, right? So that's p hat greater than or equal to 5/8. Convert it to a z-score. That's that probability. Because 5/8 z-score is 2.74. And so it's the same as what we did above.
Less than 40%.
Is there any way to plug this all in the calculator?
Yeah, that's what I'm trying to do, but it's not giving me.
For proportions, you can, but you're still going to have to find the mean and the standard deviation.
It don't get the answer?
It will give you the answer, but you still have to find the mean and standard deviation. Just like we did last time with standard normal. You still need mean and standard deviation. But I don't think we used the calculator last time. That's
No,
more advanced. Here it's all from a chart.
so now that so that problem, that one problem, that's what we just.
There was 2 parts.
Oh, the first part is to get the
This was the first part up here. And then this was part 2. Right, so there's 2 different parts in that question.
That's what I'm saying. One question.
There's technically 2, right?
So if we have like 20 questions like this, that'd
That'd be easy.
seriously.
This is easy compared to what we're doing next.
You know it, so it's easy for you. I don't know how you manage to know it like this. I don't know. I wish I could be like you, but hey, to know a math problem like this.
20 plus years.
You
I
said
know,
this
right? Thank you. Thank you. You just made a kids.
I don't know, 20 plus years.
Yeah. So you think it's gonna take us just few, like maybe 2
Well, so I'm telling
hours?
you, this is easy compared to what we're doing next.
Jesus. It can kill my vibe. This thing can kill my vibe. We're gonna fight to the last man for. He's gonna see the end. No matter what it is. At least you have made it that is high. At least.
Well, hard for the first time you see it.
I seen it.
It's still
but I didn't
easy
look at
to
it.
me.
For you, yeah.
And some of the other math courses that they may have to take. You wish you could do back to this.
I have never liked math.
That's
I
what
definitely
I learned how to spell.
seen it.
Genius, good genius.
That's actually not true.
Well, I'm gonna survive this. I'm gonna still survive.
Oh, you'll survive it.
We still living.
She said, how many others are still surviving?
Oh, everyone's surviving.
Well,
No,
they
no one's
go
actually
on.
died from it.
This plastic is smaller.
Yeah, but they're dead. They survived.
Yeah.
To nobody.
By the way, no one's actually dropped yet, though, so.
Oh, so people just don't show.
So, still a full roster.
How many more
No, he
weeks
said
we got
nobody
left?
dropped out.
4, 3? Cause I get with.
This week, 3 more plus Thanksgiving off.
Oh, hold on.
And it's how far the.
Hold
So
on.
just you.
We are on our classes.
So it's 4 weeks after this, but one of those weeks we don't need.
4 weeks, so
So
that
it's
is
3, it's 3 meetings after today.
3.
Well, 2 meetings after today, because the last meeting, the last test.
Yes, and when we're gonna have our next project?
Do you have other classes here?
Cause we got it 3 more weeks
Yeah.
other than today.
So for you,
I just wrote the slides for that, so 2 meetings from today. So not the next meeting, the meeting after is what their project is,
Oh, this one is.
So I think that one is almost gonna be like when we finish.
because it's all about hypothesis testing.
I had to come Monday and Tuesday.
But you said the third project is next week.
No, and like in 2 weeks. Like the next, not the next one, the next one, class. The 7-week class. Not this, not the following week, but the next week.
It's been found that 2% of the tools produced by a certain machine are defective. Probability that in a shipment of 400 such tools, 3% or more will prove defective, 2% or less will prove defective. What is our probability, not probability, population proportion? Yeah, 0.02. Standard deviation is the square root of p times 1 minus p, which is what? Over the sample size. What is our sample size?
So 100%.
Wait, how you got 0.98?
1 minus P.
That's how you got it right. 100%. Yeah, so that is if you have 100%. Am I right?
Yeah.
Yeah.
Because there's only 2 outcomes.
2 out of 100%.
It either meets the
So you
characteristic or
got
it
that's
doesn't.
what 98.
So 100 minus 2.
2, yeah.
Okay, makes sense.
What is that? Three decimal places. Point oh seven. We're looking for 2 probabilities. We'll start with the first one. 3% or more. What do we need the z-score of? What is it? 0.03. More than 3%. That's what I got, 1.43. So the probability we're looking for is that probability. But that's not the area the chart gives us. Be careful. You're not subtracting it by 1. You're subtracting it from 1. By 1 would be the probability minus 1. So 1 minus the area to the left of 1.43. 0.9236. That area is 0.0764.
And there's more to this problem, right?
Yeah, there's a second part to it. This was the first part. The process is the same though. 2% or less, what's the z-score? So what are we trying to find the z-score of? 0.02. Oh. Well, that's easy. What's the z-score?
0.03. Wait. There.
0.02 is the mean. So z-score is 0. So we're looking for the probability that z is less than or equal to 0. You don't even need the chart for this. What is that probability?
Look in the chat.
chart for this.
This got 0, 1.
0.5.
And how do you get 0.5 without looking at the chart?
Let's see.
Property of the normal distribution. Half of the area is to the left of 0, the other half is to the right of 0. You're symmetric about the mean, 0.
If you want us to boost it, I would agree. Just give us this. Just make a whole difference. And then we can always recommend.
Election returns showed that a certain candidate received 46% of the votes. Determine the probability that a poll of 200 people selected at random from the voting population would have, why is the space there? Happens when you use a program that's not meant to be used for typesetting. Probability that a poll of 200 people selected at random from the voting population would have shown a majority of votes in favor of the candidate. And then of 1,000 people. So actually what I have not been doing is checking, even though the conditions are clearly satisfied. I forgot to check if we can actually use this.
What you mean?
So there has to be a condition. N times P and N times 1 minus P both have to be no less than 10. Well, here, half of 120 is 60. So that clearly satisfies it. 400, what is 2% of 400? Well, 1% of 400 is 4. Actually, this one cannot be used. I'm going to pretend that we can. And 1% is 4, 2% would be 8, which is not 10 or larger. Technically, all this work is meaningless. %46 of 200, because that's what P is, right? 0.46. What's half of 200? 100. 46% is definitely going to be larger than 10. 46% of 200 will not be that much less than 100. It's not going to be less than 10, for certain. So that's good. Which means 1 minus P, 54%, clearly over 10 as well. So we can use this. This is broken, though, into 2. I'm going to have to find 2 means and 2 standard deviations. 1 mean, 2 standard deviations. Because standard deviation depends on your sample size. And we have 2 of them. So what's the mean? What is it? 0.46. It's the population proportion, which they told us is 46%. Standard deviation, square root. 0.46 times 1 minus 0.46 over sample size, 200. I'm going to go up to 3 decimal places again. .035. Probability that a poll of 200 people selected at random from the voting population would have shown a majority of votes in favor of the candidate. What does it mean to have a majority of the votes? Right, so in terms, more than half, more than 0.5. So we need the z-score of 0.5. Got 1.14. Value minus mean divided by standard deviation. Right, mean was 0.46, standard deviation was that 0.035.
You mean how did you get to 0.5? Is that what you're at? Because it needs to be more than half the.
0.5. What does it mean to get a majority of votes? You get more than 50%. Right? If you have more than half of something, you have the majority of it, right? That's what we're looking for then. Which is that probability. Area to the left of 1.14. One, 2, 7, 1. Same question. Except now our sample size is 1,000. Well, if it worked for 200, it's definitely going to work for 1,000. We're increasing the sample size. It's not going to hurt. What's the mean? It's still 0.46. Now we're taking the square root 0.46 times 0.54 over 1,000. That is going to change the standard deviation. Yeah, 0.016. Same question, so it's the same proportion, 50%. Backwards. So now the probability we're looking for is this one. Larger than 2.5. Which is going to be an even smaller probability. Area to the left of 2.5, 0.9938, right? So 0.0062. .2% chance. Which again makes sense as your sample size increases, your sample proportion tends to the population proportion. And so as we increase the sample size, it becomes less and less likely that they get the majority of the vote. Those are the two statistics that we are going to study in depth. Mean and proportion.
Like you mean for the rest of the meeting?
What we look at next is confidence intervals. Like I said, we only studied two in this course. Confidence interval for the sample mean, and confidence interval for population mean, confidence interval for population proportion. You can also do standard deviation. I remember doing that when I took stat. I remember the chi-squared test. So I don't know why it's not in it anymore. Point estimate of a parameter. is a value of a statistic that is used to estimate the value of an unknown parameter. So what we want to do is ultimately use a statistic to infer something about the parameter. So use a sample to make a conclusion, to draw a conclusion about the population as a whole. And if you're really good at this, you can make some big bucks.
Doing what?
I'll use presidential elections. They hire pollsters to infer, okay, if you say this, how's it going to look? How's it going to affect your standing? What are your chances of winning the election? So that's what I said. If you're really, really good, you can make some really big bucks. They get paid. The good pollsters get paid bucks.
Did you vote on the election day?
Of course, well, now I voted early.
No, like vote on the election, like who's going to win.
Did I vote? Yes. Did I bet? No.
Bet, yeah, bet. I'm sorry, yeah, bet.
I don't bet.
Oh yeah, you did say that. You told me
I only make bets if I'm guaranteed to win.
I know, right? Yeah.
Or if I'm just really, really bored and I have a lot of extra income to dispose of. That latter part doesn't happen a lot. Of course, you have to be careful too, because you're winning, you have to claim all taxes.
Sure.
A lot of people don't realize that, and then tax day comes and they get a knock on the door from the IRS.
Especially when FanDuel people.
And they report that shit too, so.
They do.
There's-
Yeah, they got
there's
the
no hiding.
security,
The
yeah.
IRS is going to find out.
So say if you only won like $5,000 on it, you still supposed to report that to the IRS?
You have to report it, yes.
Oh.
You're probably not going to pay taxes on it.
Okay,
because it's a relatively small amount.
Yeah, that's what I'm saying. That's small.
But, you know, those game shows where they like win cars and shit, you know they have to sell the car to pay the taxes.
Oh wow.
They don't actually keep the car unless they're rich and they can afford the taxes. Because they take the value of the car and they have to pay, I think it's like 30%.
So they're not even winning nothing.
So if the car's worth $100,000, you're paying $30,000 in taxes. So unless you just have $30,000 lying around, you're selling that car to pay the taxes.
Wow.
Which is still a net $70,000 gain, but you lose the car. And that's if you can find someone to buy it for the car value. Confidence interval is an interval of values used to estimate the value of an unknown parameter. So we can never say for certain, make a certain conclusion about a population from a sample, no matter how large the sample is. But we can kind of determine a range that this value, that the parameter is going to be in. That's your confidence interval. It's constructed using the point estimate along with a percentage called the confidence level. This confidence level specifies how confident we are that the parameter lies in the interval. The most commonly used confidence level is 95%. .95, which, if you remember, what the hell is it called now? Drawing a blank. whatever that theorem's called that says about 95% of your data is between two standard deviations, within two standard deviations of the mean.
What was that?
I don't remember what it's called. It's drawing my mind right now. Empirical rule. There it is. Right. What was it? About 68% is within 1, 95% is within 2, 99.7 is within 3. The three most common values are 0.9, 90% confidence, 0.95, 95% confidence, and 0.99, 99% confidence. Of those three, the 95% is the one that's used most often. This confidence level represents the expected proportion of intervals that will contain the parameter if a large number of different samples are obtained. Of course, we're inferring something about a population from a sample, which means there's going to be error associated. And again, if you follow polls, specifically elections, whenever you hear a certain candidate has 50% of the vote with a margin of error, that's where it's coming from. The margin of error is the error. They're inferring something about the population from just a small sample. And it's half the length of the confidence interval. Notice it's the confidence interval, not the confidence level. So once you find your confidence interval, find its length divided by 2, that's your margin of error. We begin by looking at how to find confidence intervals for a population mean. And there are two possibilities. You either already know the population standard deviation, or you don't. Realistically speaking, you never know the population standard deviation. Because if you did, you know the mean. How do you find standard deviation from the mean? But it is a good place to start. This is the rest of tonight. Finding confidence interval for population mean. First assumption, it's a simple random sample. In fact, that's always going to be the assumption. Your sample is chosen simple random. Don't worry about what simple means. Because again, that's something they don't go over sampling theory in Stat 1, which you think they would. They don't. Yes, there's a branch of Stat called sampling theory. How to actually find samples. The population is either normally distributed or your sample size is at least 30, right? So the central limit theorem is satisfied. Now what the central limit theorem said, if your population is normally distributed, then the means are automatically normally distributed. If not, you must have a sample size of 30 or larger in which you can then approximate the means being normally distributed. And obviously the larger the sample size, the more closely the means resemble a normal distribution. So it never hurts to have a larger sample size in terms of inferring something. It just means more data, which is more time and money. The population standard deviation is known, which again, not very realistic. Those are the three assumptions. Confidence interval. X bar minus E to X bar plus E. Remember, E is the margin of error. The margin of error is calculated as Z sub alpha over 2, so the Z score of alpha over 2 times your population standard deviation divided by the square root of your sample size. Don't worry, I'm going to give you some common critical values for Z. Alpha is your 1 minus the confidence level, which is going to be on the next slide. So if it's 95% confidence, alpha would be 0.05.
And E is error, right?
Margin of error.
Margin error, yeah, okay.
Yes. Right, so alpha is 1 minus the confidence level.
I'm sorry, can you go back 1 second? I'm sorry.
Can I? I can.
Please, thank you.
You shouldn't ever thank someone until after the service is completed. I learned that at a very young age.
Thank you, I'm good.
For 90% confidence, your alpha is 0.1, alpha over 2 is 0.05. So your critical value would be 1.645.
Is that a problem or it's just?
No, these are commonly used critical values.
Oh.
How we found that is you just look at what is the Z-score that is associated with 0.05 area to the right. It's between 1.64 and 1.65. That's why. Well, actually, this is actually found analytically using calculus. That exact value. 95% confidence, your critical value is going to be 1.960. For a 98% confidence, critical value is 2.326. And for 99%, your critical value is 2.576. For the most part, your critical value is going to be one of those four. It is very rare not to use 90, 95, or 99. So it's rare, very rare. It's rare not to use 95.
Not to use it, so that is.
It's pretty rare. It's pretty rare to use a confidence level other than 95%. It's even rarer if it's not 90 or 99 as well. In fact, the only time you'd ever do that is in a class. I've seen questions where like, oh, I can construct an 80% confidence interval. I'm like, yeah, that's bullcrap. No one would ever do that. But I guess they got to test you somehow. Otherwise, they get way too repetitive. Sample size. So how can we determine what sample size to use if we want a specific margin of error? This is where one of my favorite functions comes in. The ceiling function is going to be used here. Sample size required for a confidence interval for mu with a specified margin of error. N is the ceiling of the value. Z alpha over 2 times sigma over E all squared. And the ceiling function is really cool because all it does is takes your value and rounds it to the nearest integer, up to the nearest integer. If it's an integer, it spits that integer back out. Otherwise, it'll round it up to the nearest. So that's the formal definition of the ceiling function. And so let's say you calculate that value, get 101.0126. Then your sample size will be 102. Right, because it rounded it up to the nearest integer, which is 102. This might be a little touchy. Keep in mind, I wrote this before I graded the exams. Suppose scores on an exam or on exams and statistics are normally distributed with an unknown population mean, but somehow they know that the standard deviation for the population is 3 points. Don't ask me how they know that; they just know it somehow. Random sample of 36 scores is taken and gives a sample mean of 68 points. We want to construct a 90% confidence interval for the true mean of statistics exam scores. In other words, we want a 90% confidence interval for the population mean. The first thing we need to do, calculate the margin of error. What is our critical value for 90% confidence interval? What was it? 1.645. Our standard deviation is 3. And what is our sample size?
I mean, sorry, I was just wondering.
36. I probably should verify that this satisfies the conditions, and it does. Sample size is larger than 30. Can't be less than 30, so we're good.
Oh, it has to be over
It either has to be
thirty.
well, actually, there's 2 of them. This satisfies the fact that it's already normally distributed, the population. So right there, it's good. And the sample size happens to be larger than 30. So if it's not normally distributed, your sample size has to be larger than 30 or larger. Otherwise, this doesn't work. You wouldn't be able to do anything.
So the 3 is standard deviation of 3 points, right?
Population standard deviation, which they somehow know. I got 0.8225 for the margin of error. I'm going to keep that.
Let's see it.
Our confidence interval. X bar minus e to x bar plus e. Remember, x bar is your sample mean. So 68 minus 0.8225. 67,1775.
I feel 177. I got 77.8.
Did you type in the right margin of error?
Yeah, but oh no. Wait, I got 67.
Oh, this one's easy. 68 plus 8225 is 68.8225.
How would you be able to put that in on your calculator? I left my calculator on by itself.
How would I put what in?
Like the error, the margin of error.
How do I find it?
Yeah, like how would
You
you?
just type that formula into the calculator.
So I would put CI equal.
No. This is all by hand. I just use the calculator to find the values.
I wish I brought my calculator.
I'm going to show you how you can use a calculator to find the confidence interval.
Okay.
Because you can. You can use technology to do
Can
that.
you use the one that you told us to use?
Yes.
Thank you.
But for a lot of these on the test, I may not allow the you may have to. I may require you to show me the work. Use the calculator to check it, but you're gonna have to actually show me all the steps. Otherwise, you won't get credit. These calculations aren't that terrible. You don't have to find z. Z is usually given to you. The standard deviation is going to be given to you, and the sample size will be given to you. Right, generally speaking, the sample mean will be given to you. If not, you know how to find it. So here's the interpretation. And it is a very important interpretation. What we would say is we are 90% confident, or we can say with 90% confidence that the population mean of exam scores is within that interval. It is not. There is a 90% probability that it's in there. They are two different things. Right? Remember, the confidence level just says it's the percentage of intervals that would contain the mean. This is only one interval. We can create lots of intervals by using different samples of 36, of size 36. Right? We get all of those intervals, and 90% of those would contain the mean. So that is an important distinction.
This is a fuller file. See? Like this one, I can tell.
This is, well, because I'm more into the inferential than the descriptive. And
I can tell.
the inferential is my field.
Yeah, that one.
And that's also where you can make big bucks. God, you know how much businesses are willing to pay you to do this kind of stuff. We can say with 90% confidence that the true mean of exam scores falls in that interval. Right? Or we're 90% confident
So the problem is finished?
Yeah.
Oh,
that's
not-
all there is to finding
Yeah,
confidence.
that's
in.
not bad then. Okay.
Right? You just have to know what everything means, which is what makes it harder. This is a completely different way of thinking now. Because we're now inferring stuff.
So
Oh, and by the way, this is going to be used for hypothesis testing. This is the basis for hypothesis testing, which is what true inferential statistics is all about.
So what test is that? We're gonna do it where? In class?
It's what it's called. It's called hypothesis testing.
Oh, the last test we had, right?
The last test will cover that. But the topic itself is called hypothesis testing.
Oh, okay.
Right? We test an hypothesis, which is most of inferential statistics. Same question, except now we want a 95% confidence interval.
Okay, so what's the
So we again want margin of error.
So the A/2, what do that mean?
Oh dear, that is not an A. That is the Greek letter alpha,
Sorry.
lowercase alpha.
So the 2 is just a standard.
So alpha is 1 minus your confidence level.
Okay.
In this case, it's 95% confidence, so alpha would be 0.05.
Okay.
So the 2 is standard. So that is just.
So you divide it in half because what the critical value is it's the area that is to the right of half of it. Because what you're looking at is essentially two tails. You want the total area to be 0.05. But that's left and right tail.
Okay.
So it'd be the negative z-score and the positive z-score, right? So the left of the negative. So that's why we divide it in half, because it's symmetric. And then we just look for area to the right.
Yeah, I think we did a problem like that one. We gotta do that, like 2 meters.
Well, we did one today where I doubled it because of the symmetry. So that's essentially what this is. So that's why we use alpha over 2. Some texts use alpha. I do not like that. I actually do like this notation, the alpha over 2. Because it makes it easier to understand what we're actually finding. So what is the critical value that we're using? What was it?
1.960.
Yes, 1.96. Maybe we'll include a 0. I don't know how long I'll be including that 0, because I'm lazy. Well, sigma is the same, and so is sample size. .98 margin of error. .68 minus 0.98, 7.02. So 68.98.
And you get, how do you get the 1.96 over here?
That is the critical value that was given.
Where was it given at? Oh, done. Okay, thank you.
Yeah.
Otherwise, you have to find it from the chart if it's not given.
Okay.
But again, for the most part, it's going to be one of those 4 values.
Okay, thank you.
Compare the confidence intervals. Notice that this interval is larger, which makes sense.
Now that you got this 0.98,
Mhm.
so what did you do with the 1.960?
It's only used to find the margin of error.
So what did you do? Did you multiply them?
Yeah.
Did you do-
So it's 1.96 times that 3 over root 36.
Oh, 3 over 36. That's what.
Root
gave-
36.
Yeah, so that's what gave you the figure there.
That's the 0.98.
So how you came about with this one? This figure now?
The interval,
Yeah.
take your sample mean, subtract e from it. So it's 68 minus 0.98. That's your lower bound.
68. Okay, 68.
Right? 'Cause it's always going to be of this form. X bar minus e to x bar plus e. You just have to determine what your sample mean is and what your margin of error is, and then you can easily construct your interval. Right? Does that make sense?
Yeah, I understand it's 68. So here is my question. Do something like this figure down here was did you subtract it from the one of the total that you got up there, that is the 0.98?
Yeah, it's 68 minus that 0.98.
Okay.
And then 2, right? So the lower bound is the 67.02.
Okay.
Your upper bound, your upper limit for the interval is your mean 68 plus your margin of error.
Oh, I got it now. Okay, yeah, I got it now.
Right? So it's a larger interval, which makes sense. If we're increasing our confidence, then the interval has to get larger. Right, so again, what we're saying is we are 95% confident that the true mean is between 67.02 and 68.98. If you did a 99% confidence interval, that interval will get even larger. So let's come back at 740. calculator, you can also find confidence intervals on a statistics calculator. The way you do it's obviously going to be different than mine, unless you have the one I recommend. If you're going to want to go statistics, there should be an option for confidence intervals, and they're going to have several options. We are looking at the Z interval. So just click Z interval. I believe most calculators only gives you the option to use the statistics, not actually enter data. So it doesn't matter because that's what we have anyway. And they just have to enter what we have. So sigma was 3, right? Standard deviation was 68. Or not standard deviation, I'm sorry. Mean was 68. Sample size was 36. And I'm just going to use that second one. Confidence level, 0.95. All right, otherwise, just type in whatever the confidence level is.
It's to be done many times.
Yes. Main tab. I don't think Excel can do it without an add-on.
I have a quick question for you. What's the name of this that you're using? Because when I go to the tutors, they don't know, like they know the brand, but they having a hard time trying to show.
It's the TI Inspire CX2.
So if they type it in, no, like I'm saying, like the online version. Because I have the calculator, but when I be trying to have them help me, they be like, oh, your calculator is advanced. They don't know. Like, is no website?
This is the software that comes with it.
Oh, makes sense.
Which is just a calculator. Just allows me to project it.
Okay.
There's the lower limit. Which is what we got. There's the upper limit. Which is what we got. And there is your margin of error. Which is what we got. And so a good way to check that you did everything right. Yeah, it's a long one because it does give us a lot of information. Specific absorption rate for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every single cell phone emits radio frequency energy. So different phone models will have different SAR measures. To receive certification from the Federal Communications Commission, for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. The table, again, why is it put in the space there? The table that's going to be on the next slide shows the highest SAR level for a random selection of cell phone models as measured by the FCC, which means that table is probably not accurate because it's a government agency and they are very ineffective. Find a 98% confidence interval for the true mean of the SAR for cell phones, assuming that we know the population standard deviation is 0.337. All right, so most of that information is not really needed, it's just giving you background. And there's the table. This is one where they didn't give us the sample mean, we have to find it. All right. What was that, 30 of them? That's what they, is that what they said?
Not in here on top of
Oh,
Yeah.
yeah. That's why I'm not an English major or a reading major. I'm too lazy to do that by hand. The mean's 1.024. I'll let you verify that.
1 point what?
1.024. All right, so you can use Excel, calculator, Minitab, whatever you want to use to find that sample mean. I'm going to rewrite what they told us sigma was. And we want a 98% confidence interval. What does that give us for a critical value?
2.326.
We now have everything we need.
And how did you get 0.024?
That's the mean.
Oh, okay.
How did I get it? It's
Yeah.
on my answer sheet. What you would do is you add up all those values, divide by 30.
Oh, you are.
It's just the average of those values.
Okay, thank you. So say if it was 40, then you divide it by 40.
You'd add up all the
Okay.
values and then divide by 40.
Gotcha.
The frequency.
Right, so it's just average that we study. God, what was that? One, whatever it was. And there's several ways you can do that. Throw it into a statistical software. Do it by hand, which I don't recommend. Your calculator, you can just use the data method and enter all those data points to find the confidence interval.
Mhm.
It'll do the mean for you.
Yeah, that you have to go like on the spreadsheet data, right? Like,
Well, there's that, but also when you do this. Oh, not stack calculator. Oh, I could do stack calculation, but I don't want that. Confidence intervals, Z interval, data.
Oh, nice.
But then I have to define a list. Oh, that's annoying.
Oh, sorry, but you have to like.
Oh, yeah, no, I'm not doing that. I'm not
You
defining
have to write everything.
because that is a pain in the ass. Defining a list on the TI Inspire is a massive pain. I will not do that. Margin of error, critical score, times sigma divided by square root of n. .143. Yeah, 0.143. Right, so the confidence interval, 1.024 minus that margin of error. .881. Oops. To 1.024 plus the margin of error at 1.167. So we can confidence that the true, well, that's good news. Cutoff is 1.6 for validation, so that's good. Population standard deviation for the age of Foothill College students is 5 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of Foothill College students, how many randomly selected students should we survey? Oh, that's a typo. Sigma is supposed to be 15 years, not 5 years. I'm going to stick with 5 years.
That's why I was about to ask, like, you see, I'll probably.
Nah. Well, it's going to change what the answer is, but it's not a problem. I just can't use my solutions.
Oh, yeah, I have another question. Why do it be so much mistakes on the quiz? Like, it asks for like one thing, and then it'll talk about cars or something.
That's what I had ever written down too.
Yeah, I meant to didn't ask you that.
I don't like the quizzes.
I know,
But we
but
still
they
get
still
graded for
get
it.
graded. Like, it was like a couple of them. They ask questions, and then don't be related to what it's asking. So how would you grade that, being that you go in?
I have the solutions. So I just go off of the solutions.
But if it's talking about groceries, how are we supposed to find cars?
Make sure you're not misreading.
Oh,
Because
no.
I haven't seen that yet, and I read through the questions.
Oh, no.
So I don't know what quiz that was on. Now, I'm only up to quiz 6 right now.
I took a picture of that one.
So what are we given? We're given sigma is 5. We know what alpha is, 0.05. What is the critical value for 95% confidence?
One point nine six zero.
1.96. This is a value that is you're going to have nightmares about because how often you're going to be using it. It's going to get to the point you're going to be at Thanksgiving dinner. Oh, how's school going? 1.96. And we know margin of error. What's the margin of error? What is it? You said it. What is it? It's 2. Within 2 years. That's the margin of error. Sample size is the cool function. The ceiling quantity is Z, alpha over 2, times sigma over E all squared. Sigma was 5 over 2. Oh, yeah, squared. Forgot to do the squared around that.
That's the one.
So I got that to be 24.01 when you do 1.96 times 5 halves and then square it.
So,
The ceiling of 24.01. 25.
so I have a question.
Mhm.
I didn't notice the 0.5 being used.
0.05,
Yeah.
that's alpha. 1 minus the confidence level.
Okay.
What's the confidence level they want?
So, okay, gotcha.
So 1 minus 0.95. So, because they had a standard deviation of 15, the interpretation is different. Because we can only use this sample if the age is already normally distributed. If it's not, that sample is too small. To construct a confidence interval, you have to use 30 or more. Remember, it has to satisfy the central limit theorem. So your population has to already be normally distributed, or your sample size has to be 30 or larger.
So if it doesn't state in the problem that it's normally distributed, but if the sample size is less than 30, does that mean you cannot do it automatically?
If I ask you to construct a confidence interval, and the sample size is less than 30 and it's not normally distributed, then yes, the answer to that problem is cannot be done with the techniques of this course. If I'm asking you to find a sample size, we'd have to round this up to 30. If the population isn't normally distributed. Because again, all these techniques only work if your sample size, if it satisfies the central limit theorem. But it's supposed to be 15 standard deviation, which gives you a sample size of 217, which makes it a moot point. I don't know why I didn't see the 15. I just saw 5 when I wrote this. But that still gives you an idea of how the ceiling function works. You just round it up. Love the ceiling function. However, as I said, how likely is it that you want to determine the population mean and you actually already know the standard deviation? You're not going to. So it's way more likely that you're not going to know the population standard deviation. Which means we can no longer use z-scores. I give you the t-distribution. Also called the student t-distribution. So we have a variable x of a population normally distributed with mean mu. For samples of size n, the studentized version of x is t equals x minus mu over s divided by root n. And this has distribution, student t distribution, with n minus 1 degrees of freedom. Yeah, the t distribution is not as nice as the z distribution. Unfortunately, it's also way more realistic. Again, you don't really need to worry too much about that, because there's a table. Table C. Print it. Keep it with your table B of the z-scores, because that's the only way you're going to be able to do this without calculus. Properties of this t distribution. Again, area under the curve is equal to 1. Has to, because it's a probability distribution. Just like the z distribution, it extends indefinitely in both directions. Just like the z distribution, it is symmetric about 0. As the number of degrees of freedom become larger, which means as your sample size gets larger, the curve increasingly becomes normal. So if we let the sample size approach infinity, then the t distribution is the z distribution. So that green curve there is a sample size smaller than 30. You can see that's nowhere near looking normal. Now when you get a sample size that is close to 30 but larger, that kind of looks normal. That's the red one. The blue one is your normal distribution.
So wait, how do you know it's okay.
How do I know what?
Never mind, I see, because it's like the shortest one, because it's the smaller one.
The actual analysis of this does require calculus. So again, you're just going to take my word for it that this is true. There's a lot of that in the intro courses.
So now we're about to do like an intro to calc in a way.
Oh no. I mean, unless you want to.
No, thank you.
If you really want to understand where all this comes from, then yeah, take calculus. And then take a junior level stat course. So now we look at confidence intervals when the standard deviation is unknown. Simple random sample, as always. The population is normal, or you have a sample size of at least 30. So that didn't change either. The only difference is we no longer know sigma. Confidence interval. Still x bar minus e to x bar plus e, except e is now found differently. E is now t sub alpha over 2 times S over the square root of N. Also, unlike before, I can't give you a list of commonly used critical values because it depends on the degrees of freedom, which means it depends on your sample size. This is where table C is going to come in.
Oh, we did. Did we write this already? Like you showed this slide?
No. It looks similar because it should look similar.
Mhm.
Last one was if sigma was known.
Okay.
There is table. Oh, no, you can't see that. Let's fix that. There is table C. All right, so it's 2 pages. Bottom gives you the confidence level. The very first column is your degree of freedom. Which remember, degree of freedom is n minus 1. And this gives us area in the right tail, which is perfect. That's what we want anyway. So you just look for your degree of freedom, look for that row, and go to the appropriate column. But the problem here is this can only be used if your confidence level is 80, 90, 95, 98, or 99. Otherwise, you can't do it in this course. You would again require calculus or technology. So if you get a confidence level of some other than this with an unknown sigma, you're going to have to use technology to do it.
I know this is like kind of out of context, but I was sick last week, so I didn't come in. So the numbers on the left side, what do they symbol? This is the z-score basically versus z, or no? No, this.
If it's from table B, I recommend seeing me after class and I can
Okay.
go over it.
Thank you.
Let's suppose you do a study of acupuncture to determine how effective it is in relieving pain. I personally never understood how sticking a bunch of needles in you could relieve pain, but what do I know? I'm just petrified of needles, so I would never go. They'd have those needles in their eye. So you measure sensory rates for 15 subjects with the results given. We're going to use this sample data to construct a 95% confidence interval for the mean sensory rate for the population, which we're assuming is normally distributed, from which you took the data. I'll write it up here. Start with alpha. What is our alpha? 0.05. Sample size,
15.
which means our degree of freedom is what? What is it?
1.960. Oh. Sorry.
What's the 14 confidence?
Yeah,
All right, degree of freedom is 1 minus sample size minus 1.
okay.
Oh, okay. So now I got it.
This will allow us to find our critical value.
Now I got it. So that is
1.960. No.
So we have to come to table C. Look for degree of freedom 14. That row. You want, which area do you want?
Did it ask, it's actually for 95%.
So what area? Because I don't have the confidence interval. I'm going to show you how to do it both ways. All right, confidence levels on the bottom.
So is this, yeah, the 2.96. Should be.
You said it's at the bottom?
So the other first grade is 80, 90.
So what is alpha? What do we say alpha was? Divide that by 2.
It should be 25, 0.025.
There's our critical value, 2.145.
Do you
Scroll down, there's your confidence level, 95%.
Oh. Okay.
So I was finding it with the area.
Okay.
Okay.
There's our critical value. Right. Again, you can't use that for every problem because it depends on your degree of freedom. So you're going to have to use this chart.
So what are these numbers then?
This, below all that, is the data. That is how we're going to find the mean and standard deviation.
Oh, so we got a second part to that.
Well, now we have to find x bar and s, right? The sample mean and the sample standard deviation. Right, which can be done using Excel. Where is it on here? Oh, you suck.
You get this one, because I'm gonna say
If you find the mean, it's going to be 8.2267. So again, mean out of all the values, divide by the total number there are. So add them all up, divide by 15. Standard deviation is that really pain in the you-know-what formula from week 2. Or just use technology. We should get 6, 7, 2, 2. Those are the values we need.
So what did you just say?
Huh?
Divide that by what, 15?
To find the mean?
So you talk something about 15.
Yeah. To find the mean, add up your values,
Uh-huh.
divide by 15.
Which was this total? This 2.
That's what this here is.
Yeah,
That's your sample mean.
divide by 15.
No,
Right?
no. That is
Oh,
already
the
divided
after,
by 15.
after
yes.
you divide it. Okay,
And
so
then-
because they are 15 values.
And then the sample standard deviation, which again, I would just recommend plugging into some kind of statistics software to find it, rather than using that nasty formula. Right? And then margin of error is the same. It's just you're using the t critical value instead of z, and using sample standard deviation instead of population. 8.9261 is what I got. And then the confidence interval is found now the exact same way. Take your mean, subtract E. That's your lower limit. Take your mean, add E. That's your upper limit.
What?
E.
E.
Margin of error. All right, so we said the mean was 8.267. $7.3006. Oops. As the lower limit, and the upper limit I got 9.1528. So there is our 95% confidence interval. Oops, wrong screen. There we go. That's the one I want. So we're going to go to the same place, except now you look at the T interval instead of the Z interval. Again, I want stat. All right, so now we just enter the statistics. So X bar was 8.2667. Oh no, 2267. Standard deviation was 1.6722. Sample size was 15. We wanted the 0.95 confidence. Okay. There's your lower limit. There's your upper limit. All listed out for you. So again, really good way to check your work. Huh?
You don't have the time to verify all that, except maybe for project proposals.
What do you do? It doesn't take that long to type it in to verify your math.
Well, that's for the few.
So then maybe what you would do is you'd wait till after, and when you have time, if you have time left over, you go back and
So what is,
verify it.
so that is if you want to use it now for maybe for the career purpose.
Oh, for career purposes?
Yeah.
You wouldn't even use this calculator.
Oh really?
There's a lot of statistical software out there. The most commonly used one is R. It's the one I use. Yeah, I don't know of any serious company that uses Minitab. Or Jump. JMP, that's another one that's used.
John.
JMP. That's another statistical software like Minitab.
Oh.
They do use Excel, but really not for statistical analysis. Excel is really just used for spreadsheets, keeping spreadsheets and maybe basic statistics. But a lot of companies use R for the actual analysis. That's what I use. I love it. If I could, I'd teach it. They don't want me to. Again, another one with a lot of
Explanation.
yes,
Confusing.
explanations.
Confusing.
What is this stony with?
Human toxone. I think that's how it's pronounced. Toxone. Yeah, pretty sure it's toxone. Toxome would be a cooler way of saying it. So, Human Toxone Project is working to understand the scope of industrial pollution in the human body. Industrial chemicals may enter the body through pollution or as ingredients in consumer products. Speaking of ingredients in consumer products, how many of you wash your fruits and vegetables when you get home? You really should.
Why?
Oh, I worked produce for 10 years. Do you know how many times we drop stuff on the floor and just pick it up and put it back on the shelf?
Yeah,
We do it
people
by-
touch all over them. So yeah,
Yeah, plus, generally speaking, we're not wearing gloves because it makes it harder to actually stock with gloves because you can't feel anything. And while we do our best to wash our hands all the time, we still have to get from A to B. You should- Plus, the trucks are filthy. You should
Yeah,
wash
they be
your-
peeing in the trucks.
Yeah,
and
you should really
everything,
wash your-
yeah.
wash your produce.
Mm.
Unless you like to live dangerously like I do.
So when you clean your
I've also seen produce come in with a bite taken out of it.
from a mouse, yeah.
No. A human bite.
Oh.
Yes, I've also had produce come in with snakes and spiders,
Yeah, that is good.
Mice.
With a bite.
all kinds of rodents. The snake one was fun. That was fun to watch my coworker jump and scream like a little girl. That was really fun. Just got me back because then I got a spider and that made me scream.
I step on a snake before.
Yeah, okay. Until you're not expecting it and the freaking thing jumps out at you.
Yeah, I just played with a mouse, and I was gonna kill this mouse. When I lifted my feet up, it was a snake on my feet. It
Where are you from?
was Africa.
West Africa. What country?
Like
Liberia.
Black Mamba.
Yeah.
The scientists at HTP tested cord blood samples for 20 newborn infants in the United States. All right, so the cord blood of the in utero newborn group was tested for 430 industrial compounds, pollutants, and other chemicals, including chemicals linked to brain and nervous system toxicity, immune system toxicity, and reproductive toxicity and fertility problems. All right, there are health concerns about the effects of some chemicals on the brain and nervous system. Blah, 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 blah. Table here shows how many of the targeted chemicals were found in each of the infant's cord blood.
So should we add them all up to
20, yeah.
and divide it by
You're
20?
going to have to.
Okay.
Use the sample data to construct a 90% confidence interval for the mean number of targeted industrial chemicals to be found in an infant's blood.
Hold on. You were reading another question first, or that's the same?
See? It's all part of the same question.
Oh, okay, so it just wrote
Right, again, all of this is kind of like prelim.
background, like
Yeah. The only thing important here
it's the 20.
is the 20. So there are two answers to this. One, if this was a test question. If this was a test question, your answer is it cannot be done.
It can't.
Nope.
Why?
Sample size is not greater than 30.
Okay.
It's less than 30. And they don't tell us that the population is normally distributed.
Oh, in this one.
So we won't be able to do it. I am going to go under the assumption for the sake of class that the population is normally distributed.
And
Just
so
we can
we're
do this.
dividing this by 20, right?
You'd wind up dividing the sum by 20.
127.45.
What was it?
127.45.
That is the mean. Not there yet, though. I'll put that for just to have it. What's our alpha?
Alpha is 0.0.
0. Point what?
And then it's 26.
0.1.
Oh, okay.
10%. Sample size is 20. So what is our degree of freedom?
It's 19.
19.
Good job.
This now allows us to find our critical value.
And she got 19 because, what did you do?
Minus 1.
Degree of freedom, 19. Alpha over 2 is 0.05. Critical value is 1.729. Again, if you scroll down, you'd see this is the 90% confidence. So 1.729 will be our critical value. Table looks intimidating, but it's very easy to read. Since you were so enthusiastic to get the mean, what's the standard deviation?
One second.
It's going to take way more than a second.
I don't have the proper calculator with me right now.
My calculator always, I don't know how to use it for that.
25.965. For the test, I'll try to give you the standard deviation, the sample standard deviation. Maybe for one question I won't, just to really test you. But for the most part, I'll try and give it to you.
Usually not, but that's what's
I
like.
may not give you the sample mean, though, because that's easy enough to find. If it's a large sample, I will.
No, you should help us get points.
You realize that's just going to make it less points
Oh,
that the
God.
question is worth if I'm not making you find the mean.
So when is the last test? Is it
It's the
going to be
last,
the last
it's the last official mean.
or the last that we're going to read?
Not during the exam week.
So how you? Oh,
I don't know what the day is. December.
oh.
You'll know. I'll tell you just like I did before when the test is coming.
Yeah, well, we got 3 more times to meet, right?
So it's that last one.
So wish me we don't stand a better chance.
I remember there is a week off in there.
Yeah, wish me we don't stand a better chance. Like, maybe just give us less questions and give us more time to. Gonna help us.
At margin of error, T alpha over 2. I'm not going to write that out for the sake of room. 1.729. So critical value times standard deviation divided by the square root of our sample size. What does that give us? $10.5 is what I'm going to use. One more decimal place and the largest number of decimal places in the mean and the standard deviation is typically what I use. 0.385. confidence interval. $117.4115 to 137.4885. Maybe the project's assigned next week. That's right, 'cause I actually fell behind. That's right, I just wrote next week's. It is next week. The project will be assigned next week.
Yeah. So when's gonna be Sunday?
2 weeks after that.
So that is the last week.
I'll
Cause I'm calculating, we have
have to get,
3 more.
I'll have to get back to that.
Yeah.
Because I don't remember if I counted Thanksgiving week as a week for you to work on it or not. It's in the syllabus for the due date. I just don't remember what I put down. I think it's December 2nd.
Okay.
I think that's what I put down.
Yeah, cause we still have time.
Questions on confidence intervals so far? This was just confidence intervals for the mean. Next week we do proportions and start hypothesis testing, which is exciting.
Oh, wow. It's exciting. That is exciting about statistics to me right now.
See, I said the same thing until I learned all the uses. Once I got more advanced into my research and stuff, and I saw how often it's used.
So class is over?
Not quite yet.
Wow.
Oh, we thought you like us to do.
So first, let's look at that. All right, quiz 9.
Assignment.
Now, one moment, you've all been waiting for it.
Project.
Nah, I don't want to see that thing.
Yeah, yeah.